Good morning or afternoon or night, depending on when you're watching my video. Um, so last class, you guys did some work with ice core data, and I gave you real data from a real ice core that you got to explore. And today, at the beginning, I'm going to kind of go over that to make sure that you understand what you were looking at. But I was really surprised that a lot of you hadn't actually heard about ice cores before and about how that's how we know what the climate has been like in the past. And I have a lot of friends that actually do that research on uh, ice cores. So I would have loved to like bring them into class or something, but unfortunately we couldn't do that. But I asked one of my friends if she had any cool resources that she could share with us, and she shared this really cool video of one of her professors who went to Antarctica and dropped a chunk of ice down one of these holes. So I'm going to share that video with you guys as kind of our warm up, fun, cool ice thing for the day.
Would you play it again just to remind me of what it sounds like?
Yeah.
I remember that it made a weird noise, but I don't really remember what.
Oh, it's weird. Yeah. Hey, I'm Peter Neff. I'm here at La Dome. We're drilling a whole bunch of ice cores to pull out ancient air, study how the atmosphere cleans itself. So the most recent work that I've done is with the air bubbles that are trapped in the ice. We have ice that can be up to 800,000 years old. Just like tree rings, we can build records of what climate was like in the past. Once you have all of these boreholes that you're done with, you've done all the science. The logical human thing to do is to throw some ice down a deep hole to see what it sounds like. And that's what we did. It's just like an unexpected sound. It's a solid ice borehole. I mean, this is the video, the version of it that went viral, and it's beyond 10 million views now. And the first thing you hear as ice is falling, the pitch of the sound is changing, and that's the Doppler effect. And then when the ice hits the bottom of the borehole, the sound doesn't only come straight up. The sound waves start to bounce off the side of the hole, so that's why you hear this ping. And then there's a sort of a heartbeat sound afterwards. Yeah, I'm big in Japan. I was interviewed on the national broadcasting. They even made an animation of the ice drop, and I think they got all the acoustics right. That's incredible. It's great to be able to share about Antarctica from Antarctica now. It takes a long time for us to get scientific results, so videos are nice to share in the meantime. Like the ice drop video is a little disconnected from the science, but it's an entryway for people to see what we do. And it's sharing with people the work that they help to support.
I think that is like the coolest thing. There was also another movie that I wanted to show you, but just for the amount of time, I'm not going to put it in this video, but I will put it somewhere in a link or maybe in the announcements for the day where you can go click on it and it will show you them working on it in Antarctica. And it's so cool because they have to work in a lab where they are in full snow gear because they have to work where the ice is going to stay frozen. Um, so they have to do all their experiments like in a huge freezer, which is really cool. There's also in this other video, there's some people from Dartmouth College in it, and they show you how big the ice core ends up being, like how many boxes this ice core has to go in. So it's really cool. But for our general knowledge, what I wanted you guys to work on last time was looking at an ice core um, just like scientists do. And I know it might have been a little confusing, but I wanted you to get a feel of what scientists, when they do this real research, like what kind of data they get and how they make decisions and how they can say that climates are changing. So I'm going to really quickly now go through some of the lab that we did, some of the TUVA activity that we did last time, and explain some of the things that are inside of it that you all had so many questions about. This was the first graph you were supposed to make. So to quickly orient yourself again, on the x-axis is the years before present. 0 would be now, and 160 on the left would be 160,000 years ago. The dark blue is the temperature, and the light blue teal is the dust concentration. And both of those are measured in percent different from the mean. So if you didn't understand what that was, basically this horizontal line on the 0 coming off the y-axis gives us the average of the temperature, the dust, the CO2, the methane over the last 160,000 years. So that's the average. So obviously, if any of these lines go above that, that's more than average. So more than average temperature, more than average dust concentrations in the air. And if they go below it, then there's less than the average. So this is just a really great way to be able to quickly compare data by looking at it against a mean. So then you can start thinking about this as which one is affecting the other one. So if the temperature goes up, does that mean that the dust is going to go down? Or is it the other way around? When the dust goes down, the temperature goes up. I'm not going to lie to you. This is something that scientists debate a lot. The general consensus in this one is that it is the dust affecting the temperature. So when the dust amount in the air goes down, the temperature will increase. And when the dust amount in the air goes up, the temperature will decrease. It will get colder if there's more dust in the air. And scientists are able to say this by looking at the data. And in this graph, it's not so clear, but once you get deeper into it, scientists are able to see that the dust actually happens first, and then the temperatures follow that. So that's when scientists are looking at this data, they're trying to figure out which is affecting the other ones. So I'll tell you why this happens. Why does the dust influence the temperature? So today, talking about the sun's energy is going to be like the main idea pretty much of the whole lesson. So, sorry, you can't really see my beautiful drawing of the sun up here because of this thing from my window, but there's a sun, and then we have a nice little landscape. So we all know, the sun shines on the planet and is giving us energy. And sometimes we capture that energy and create solar power, but basically the sun is giving us energy. But we are also giving energy back to the sun in a way. So as much as we get, we are giving away. So basically what's happening is sun energy is coming in, it hits things, some of it absorbs, but it also reflects back. So the energy, sorry, this is really hard to see. The energy that is coming in comes and then it reflects back. This is called sunlight, which we've obviously heard of before. This one is called earthlight. It's kind of cool. Probably haven't heard of it before. Don't really need to know it too much, but I think it's a really cool word. It's called earthlight. Because we can't just take energy from the sun. If we just kept taking all the energy from the sun, we would be really, really, really hot. So the sun, Earth, and space are kind of acting in homeostasis. The sun is giving us energy, and we are emitting energy back out into space so that we stay at an equal balance. Okay? So this is a concept that you need to understand for this entire lesson. So if you didn't get it, go back and listen again. We are getting energy from the sun. We are giving that same amount of energy back. And because we are in this equal balance, we stay at relatively the same temperature. Okay? So keep thinking about this coming in and going out as we move through the lesson. There's my eraser. So now we need to talk about the dust thing. So the dust that they're talking about is really like dust that's coming out of volcanoes, or things that would be putting minerals and dust into the air. Maybe a asteroid hits, something like that. So there ends up being all these dust particles that are in the air. I'm going to draw them really big so that you can see them. So we have all these dust particles that are floating around in the air. This is when the mean is higher. There's a lot of dust. So what's going to happen to the temperature? Lots of dust. Right. So there's going to be, if there's a lot of dust, the temperature is going to be lower. So how does that actually work? What's the science behind it? So as the sunlight is coming into Earth, it's going to eventually be reflected away. But if it hits all these little dust particles, it doesn't actually make it down to the ground to be absorbed as heat. So the sun comes and it just gets reflected off of these dust particles, and very little sunlight is able to make it through the dust particles onto the ground. So all these dust particles are basically intercepting the sunlight and not letting it reach the Earth. And that's why it gets colder here. On the opposite side, if there are like the mean amount, the regular amount, whatever regular is, amount of dust particles in the sky, some is able to come through. Some sunlight is able to come through, and some of it gets reflected away. And if there are very little dust particles, all of this sunlight is going to come through and hit the Earth. So dust actually acts as like a physical barrier that blocks the sun from coming and hitting the planet. All right, so hopefully that part makes sense to you. If you are critically thinking about this, though, you should think that, okay, if there's more dust in the atmosphere, that's going to block more sunlight, but that would just keep us at like a steady temperature, right? It wouldn't make us get colder, because it would just be like we were getting less sunlight every day. So we would just be the same amount of cold all the time. But it's not. On the graphs, we see it gets cold, and then warm. It doesn't like really even out. So we need to figure out why. And the answer is positive feedback loops. I've already set you up for it. One of the main things that determines how much energy is going to be reflected back into space is color. So a new vocab word that you'll need to know is albedo. Okay. Albedo is the amount of sunlight that gets reflected off of something. So normally, if we were in school, we would do a lab on this. But you have enough life experiences that you can kind of observe this on your own. Because you know that if you go outside on a hot sunny day and you wear a black outfit, you're going to feel really warm because you are absorbing a lot of heat. Whereas if you go outside and you wear a white outfit, you're actually going to be reflecting away a lot of the heat. And that has to do with this word called albedo. So basically what's happening is you're absorbing heat, or if you're wearing a white shirt, lovely shirt, I know you have all missed my drawings. When the sunlight hits the white, it actually reflects away and it doesn't soak in and absorb. So as the sunlight comes in, it basically all gets reflected away. So the shirt, which is reflecting pretty much all of the sun's energy, has a high albedo because it's reflecting a high amount of energy away. And a black outfit or something really dark would have a low albedo because it's reflecting a low amount of energy away and you're absorbing all of that energy. So this concept is really, really, really important in the polar regions of the planet. Because why? Because that's where we have those ice caps. And ice caps are white. So let's explain how a positive feedback loop can occur here using this new word, albedo. So drawn here, I have a beautiful area of a polar region. Obviously, there's the white snow cap area, glaciers, and then there's the dark ocean. So which part of this landscape is going to have a high albedo and which part is going to have a low albedo? So the white ice caps will have a high albedo. They will reflect most of the light back. The oceans will have a low albedo. And when they take in energy, they'll hold on to it. And because it's an ocean and has a high specific heat, we know that it's really going to store that energy. So now we can start talking about the dust situation. So a lot of dust ends up in our atmosphere because there was a huge volcano. So all this dust is in the air, it's interfering, and it's not allowing the ground to warm up really. And we know that because all of this is going to be reflected away, and only a little tiny bit can make it through, the temperature is going to get colder. So if the temperature gets colder, what's going to happen to our nice ice cap here? Yeah, the ice cap is going to get bigger. So we're going to get rid of some of our ocean here, and we're going to make our ice bigger. That means that now any sunlight that makes it down here, even more of it is going to get reflected away. So that's going to make it even colder, which will make it there be more of an ice cap. Sorry, I don't want to draw over this. Now hardly any is being able to be soaked in. Most of it is getting reflected away, and that makes it even colder. So we can see how we have a positive feedback loop here where we're moving colder and colder and colder. Then, of course, I know what your next question is going to be. So if it keeps getting colder and colder, how can it ever change and get warmer? And that question is honestly something that people still argue. Scientists are really still trying to figure out how we can go from something that has a positive feedback loop of being cold, 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 and then suddenly switch and become warmer. Yeah, there's lots of different people's ideas out there, and they're still trying to prove them through different pieces of evidence. But maybe all of this dust settles, or other people say that the orbit around the sun changes and everything lines up, and we start to get warmer. So all this dust goes away, and all the dust settles out, and now all of this sunlight can come in. So the planet is going to start warming up, and then we start a positive feedback loop in the other direction where the Earth is warming up, so that melts this amount of ice, and that means that it's going to become ocean. And that means that more sunlight is going to be absorbed here, and that's going to warm it up. So that's going to be even less ice and more ocean, okay? Etc., positive feedback loop. So albedo, with ice having a high albedo, oceans having a low albedo, has a real impact on temperatures on the planet. So that was just dust. Now we can start talking about the other things that we learned about on the tuba, like the carbon dioxide and the methane. And those are things you've probably heard of before, and you've probably heard of the word greenhouse gas before. So let me explain to you what a greenhouse gas is and why they're actually good. So before I tell you like how a greenhouse gas works, let's just get some of the most common ones listed up here. So the one we've all heard of before, carbon dioxide, methane, cow farts. Water vapor is a greenhouse gas. Ozone is a greenhouse gas. And nitrous oxide is a greenhouse gas. And I just said a second ago, if you caught it, that greenhouse gases are good. And I stand by that. Let me show you why. So we're back to this picture of the sun coming in and hitting the planet. And I told you that the amount of sunlight that is coming in is going to be equal to the amount of energy that we are giving back to space. Okay, otherwise we would just be getting hotter and hotter and hotter and hotter. So the energy is coming in as sunlight, and it is returning to space as Earth light. Now, if this were the case, during the day, we'd be fine. Sunlight's coming in, things warm up, and we're giving away that energy. But there would be a really big problem at nighttime because there wouldn't be any heat at all. There would be no sun, which means we wouldn't be giving away any heat, and we would be frozen. Like, we wouldn't have anything. I know it gets cold at night, but it would be like being on a different planet cold at night. Greenhouse gases are actually what keep us warm. And I told you when we started the atmosphere lesson that the atmosphere keeps us warm. Okay? Otherwise, it would get really, really cold at night. So greenhouse gases are super important because they keep us warm. If we didn't have greenhouse gases, the average temperature on Earth would be 0 degrees Fahrenheit. It would be really, really cold here. It would be hot during the day, and it would be really freaking cold at night. So let me explain how the greenhouse gases keep us warm. So if we have our greenhouse gases floating around, here's some water vapor, here's some carbon dioxide, and I'm just going to put these ones up for now. Okay. There are other ones, but so the sunlight is coming in and it is reflecting back and trying to get to outer space. And I just said that if that were the case exactly perfectly, it would be really cold at night. But what happens is this sunlight comes in, it reflects back, but when it hits a greenhouse gas like a water vapor or carbon dioxide, this actually warms up. So this sunlight hit the ground, reflected back, and it warmed up this water vapor. Here's the important part. This greenhouse gas is now able to re-emit back down. Okay? The same thing happens to this greenhouse gas here. The sunlight comes in, it reflects back, this warms up, and it's able to send energy back down. Comes in, goes up, hits this one, it reflects back down. It doesn't always reflect back down. Sometimes it'll find a gap and it will go right to outer space. It'll come down, go back into outer space. But once in a while, it will come down, hit a greenhouse gas, and reflect back down. This means that at nighttime, even though there is no sun, we still have heat because these greenhouse gases are re-emitting their heat. So this might happen during the daytime, but coming back down happens at night. So these greenhouse gases are able to keep us warm by basically re-emitting the sunlight at nighttime. I know that's really complicated. It might make sense for you to watch this part of the video again, just to get the idea that not all the sunlight is going out. Some of it does, but some of it hits these gases and gets re-emitted back to us, and that keeps us warm. I just said that if we didn't have it, we would be at about 0 degrees Fahrenheit because at night we'd get super cold. With greenhouse gases, the average temperature on Earth is about 60 degrees Fahrenheit. So these keep us 60 degrees warmer than we would if we didn't have them at all. So here's another example of how greenhouse gases work that you may have experienced before. So obviously there are different types of nights. There are humid nights and there are dry nights. And you know those humid nights, they're really sticky and they're hot, and if you're camping, you can't sleep. Um, you could also, if you wanted to, you could compare relatively between Vermont and a desert. Vermont is obviously going to be a lot more humid than a desert, which has hardly any water vapor in the air. So on a humid night, there's tons of water vapor in the air. And theoretically, it would have had this water vapor during the day as well. Okay. Whereas in the desert, there might just be one water vapor. Okay. So during the day, the sun is going to shine. It's going to reflect back. And these are able to heat up during the day. And at nighttime, they're able to give off that heat back to you. So, So at nighttime, even though there's no sunlight, these little water molecules, the little water vapors, are able to give you back heat. And because water has such a high specific heat, it's able to hold on to it for a long time, all through the night, and give you that heat in the night. In a desert where it's dry and there's hardly any water vapor, it's going to be much colder. Okay. So on a humid night, it's really hot because all this water vapor is giving you back the heat from the day. And on a dry day, there's hardly any. This happens a lot in the winter. If you've ever gone out in the winter, a lot of times it's actually really dry and it's really cold because there's no water vapor to keep you warm. So it's a really cold night. There's hardly any water vapor, and you can see the stars, and it's really great. You're probably under a high pressure system, and it's cold because there's not a lot of extra greenhouse gases giving you warmth for the night. So greenhouse gases are a good thing. They are a part of your everyday life. They make it so that we can survive here on Earth. But, of course, there's a but, because I can't be your earth science teacher and be telling you greenhouse gases are great. Too much of a good thing is not a good thing at all. Even though I will admit too much of dessert is a good thing until my belly hurts at night. So now at this point, I've explained to you why the dust impacts the global temperatures, and you should be able to explain why, when there is an increase in carbon dioxide and an increase in methane, there is an increase in temperature. Because just like the gases, scientists have been able to determine that what happens is first there is an increase in greenhouse gases, and then there is an increase in temperature. So it is the greenhouse gases that impact the temperature. So here I'm giving you a second to explain to me why we observe those patterns in the TUVA activity. So basically, you should be comfortable now explaining what a greenhouse gas is, why it's good, and why more of it is not good. So basically, to quickly reiterate, sunlight is coming in and it's trying to go back out into space to keep a nice balance. But sometimes it will hit and it will absorb into a greenhouse gas and re-emit down onto our planet. That's a good thing because it keeps us about 60 degrees warmer than if we didn't have greenhouse gases. So the sunlight is coming in, it's going out, it's coming in, sometimes it'll hit, and it will be re-emitted back down towards the Earth. But if we start putting more greenhouse gases into our atmosphere, suddenly all these pathways for the heat to escape, they start getting filled up. So if we drive our cars and don't pay any attention to the amount of carbon that we're emitting, we start having more and more places in our atmosphere fill up with these greenhouse gases. I'm just using carbon dioxide as an example. So now basically it's clogging up all those places where the heat would be emitted into space, And instead of that heat being emitted, it gets trapped and it gets re-emitted back down to Earth. So here, now instead of this escaping, it's going to come back to the planet. Instead of this one escaping, it's going to come back to the planet. Same with this one. It's going to come back. There are still spaces where the heat is going to escape, but with more greenhouse gases, you're basically plugging up those holes and you're going to have more heat coming back towards the Earth. That's what greenhouse gases are. And that's why it's important that you understand they're good, but they're also, too many of them is not good. And so that you can explain to people what greenhouse gases are actually doing. How are they heating our planet up? What does this extra carbon dioxide in our air actually physically do? So I hope it answered some of your questions from the TUVA activity and maybe also some of your just general questions about greenhouse gases. We're going to be exploring them more on Thursday. So hopefully you're feeling a little bit more confident with this stuff than you were on the TUVA activity. But it's always good to be confused at first, because once you get it, then it'll stick with you better. So you guys are doing a great job. Thank you for sticking with everything. I know that things are complicated and TUVA is confusing sometimes, but you're doing a great job. And I miss you all. And I wish we could be in school talking about this stuff, because I don't know if you can tell, but I'm really passionate about it. Miss you.